I decided my path for doing that was to go into spaceflight. Save the planet by leaving it, I suppose. But then, circumstances changed, and then I started working on Earth observation. And it opened my eyes to what you can do with remote sensing and satellites, and what you could see and learn about the Earth from looking at it from space. And so I decided to go back to school, and I rethought of what I talked to my mom about, and I decided to go back to school, and I had become a scientist.
The hours are long and the work is hard, but these explorers wouldn't have it any other way.
This is really, tough country. It's really rugged, but it's also a very beautiful country. I think I can speak for nearly every scientist that I've worked with. They do this because they want to help. They want to provide the information and tools to solve problems.
NASA is a big and capable organization, but Earth science is a subject far too big for one country, one agency to tackle all by itself.
After nearly a decade of planning, this field campaign happened to be here just as an unusually dry season led to some of the most intense and large fires the region had experienced in the last 5 years.
We came here to look at the transport of smoke and what smoke does in the environment, particularly as it impacts clouds. And we had an amazingly intense smoke event that carried very high concentrations of smoke into a place called the Sulu Sea.
You might be surprised to learn that fires affect cloud formation, and NASA is studying that dynamic relationship.
NASA is a big and capable organization, but Earth science is a subject far too big for one country, one agency to tackle all by itself.
And when you can't do it by yourself, you call up your colleagues halfway across the globe. We're in the Philippines to better understand how tiny particles from smoke and pollution affect cloud formation. The campaign is called the Cloud Aerosol and Monsoon Processes Philippines Experiment, CAMP-X. The 2 is silent. That's just a joke, but the acronym, that's serious. This project has implications for millions of people.
I'm the program scientist for CAMP-X, and while I'm here, I'm sort of the decision maker of last resort if something comes up.
We caught up with Hal between meetings in the hangar. Along with Jeffrey Reed from the Naval Research Laboratory, he's responsible for overseeing this large collaborative effort in real time, making sure the team is meeting their scientific goals while also keeping researchers from institutions around the US and the Philippines working together smoothly.
A critical part of the process was the relationship built through time. That relationship enabled us to really work together and think about what would be the questions that would be relevant to us in the Philippines and in general to the region. I'm Gemma Teresa Narisma, and I'm the Executive Director of the Manila Observatory.
The Manila Observatory, along with NASA, the Naval Research Laboratory, and a handful of university partners, are using 2 research planes and measurements from a ship to look at the properties of clouds to improve satellite measurements in the region.
Satellites find it difficult to see, quote-unquote, this region, and regional climate models are having a hard time capturing these processes.
That basically means planes, ships, and teams on the ground need to fill in the missing details. Which brings us back to the most intense fire season in 5 years.
We were able to get the P3 into that smoke and make absolutely unique and important measurements.
It's important because if we cannot get the historical observations in our model, then we're not so certain whether our climate projections are correct.
When the planes aren't flying, the science teams and flight crews take turns visiting local schools, from elementary up through university.
Elementary school students can understand remarkably complicated concepts. And so it's kind of fun to introduce them to things they may not have known or thought about before. And it's remarkable how quickly they pick up on it.
At these schools, the scientists are treated like rock stars.
We've had just an amazing response from the Philippine students. Many autographs and more selfies than I can count.
Some even said that they want to become meteorologists themselves to help carry on the study of our home planet and how it's changing.
I feel hopeful. We're not getting any younger, and the number of atmospheric scientists in the Philippines, in the world, particularly in the Philippines, is quite small, and the kind of work that needs to be done to understand the different atmospheric processes in the region is quite a lot.
We are so dependent on this earth because we live here, we have to breathe here and find things to eat here. It's important that we understand it so that we don't inadvertently cause damage that could affect us all.
What we're seeing is that areas that have been flammable are becoming more flammable, pushing those systems into either extreme conditions or a year-round fire season where fires are literally possible at any time. I think the choice to study fire generally is a bit of an occupational hazard. It's true. We're not necessarily looking at the verdant green parts of our planet. We're headed to the end of the road. We're looking at areas of rainforest that have been cleared and burned. We're capturing scorched landscapes.
In this series, we've been following the fire season around the world. First in the American West, in the early part of summer, the start of the fire season. Then in high northern latitudes, Canada and Alaska. Then finally in the Philippines, as the summer became fall. In the past, you could count on the fire season eventually coming to an end. But we're now learning that that's not really the case anymore.
What we're seeing is that areas that have been flammable are becoming more flammable, pushing those systems into either extreme conditions or a year-round fire season where fires are literally possible at any time.
We caught up with Dr. Doug Morton to find out the extent of the damage.
Hotter and drier conditions, adding wind, you end up with fires that are moving faster and burning hotter than what we've seen before. Can we better understand, anticipate, and characterize the changes in our planet that come from those extreme fires?
Actually, yes, we can.
Myself and my staff at the GIS Center worked closely with colleagues at Goddard Space Flight Center to make this thing happen.
This is Keith Weber, the wildfire rehabilitation expert that pioneered a new groundbreaking tool. The Rehabilitation Capability Convergence for Ecosystem Recovery includes a function that allows fire responders to triangulate their wildfire response. The tool can geolocate everything from burned areas to potential landslides to impacts on endangered species. But Recover really gained momentum after one fire in particular.
I remember looking at our whiteboard that shows all the real high priority things we need to be doing. And that whiteboard was clear. And I was walking out, I talked to some of my students and I said, I think the wildfire year is done. We got it wrapped up. Well, shouldn't have said that, because the next day, one of our users in California, Woolsey Fire started going. It became much larger than I think they thought it would because of those big winds, and it really grew very rapidly. Well, at that point, we were working with that team on a daily basis, doing refreshes, as we call it, as the fire grew and grew and grew every day until we had that thing out.
Keith's team is making a tangible difference by saving property, resources, and lives. Innovations like these represent a promising future.
As we move from today's cutting-edge science into tomorrow's prediction, response, and understanding, the work we do today opens up an opportunity to do that so much better going forward. There are so many science topics that today are on the cutting edge of our understanding, and what get me and my science colleagues motivated to go out into the field and keep working on these problems. Can we improve the way that we can forecast, for example, fire risk, not just for tomorrow, but for 10 days from now, that might help managers, communities, prepare and respond to changing fire weather conditions?
Like all of us, our NASA explorers and partners in exploration face the daily decision to either choose apathy or get to work. The future is uncertain, but we choose to meet the challenges of this new normal head-on.
Advanced Air Mobility, or AAM, is this vision of a new mode of transportation that will enable the safe and efficient movement of people and cargo by air to and from locations that are currently only accessed by road. One area the NASA team is researching is passenger ride quality. NASA's Advanced Air Mobility mission is researching what ride quality could be like for passengers traveling in eVTOL aircraft to make sure it'll be a smooth and safe ride. The idea is to conduct research on human subjects by studying their physiological response to the types of low-frequency motion, vibration, and noise stimuli that we expect AAM passengers will experience. We believe AAM aircraft will need to be designed smartly. They will need to be conducive to low cabin noise and low vibration from the rotors. They will need to be more resistant to being upset by turbulence. And they will need to be operated or flown in a predictable, repeatable, non-aggressive manner that will not result in large accelerations or sudden accelerations or rotations of the aircraft. It's really exciting to see the amount of innovation that is going on in the aerospace industry. It is truly a fascinating experience to see all these new designs come forth.
Since the dawn of humanity, we have looked to the stars and dreamed of bridging the gap between the Earth and the cosmos. In the 20th century, NASA turned that dream into a reality by launching humanity into a bold era of scientific discovery. As pioneers of space travel, our best and brightest designed and built everything from the ground up, from launch pads to rockets, all of which were government-owned and operated. As NASA's science and robotics evolved, we encouraged a competitive launch market to develop, ushering in a new way to explore and discover through commercial spaceflight. Spacecraft customers from around the world, all with the same desire, reached out to find an expert at NASA for support. Thus, NASA's Launch Services Program was born. Our mission is to centralize NASA's launch services and address state-of-the-art customer needs when placing their spacecraft in orbit around the Earth, the Sun, or destinations deeper into the solar system. The LSP family is made up of a diverse tapestry of government and contractor engineers, analysts, operation experts, and business advisors, all united by a common goal: to get your spacecraft off the ground on time, on budget, and successfully to its final destination, wherever that may be. We match scientific and robotic spacecraft with the appropriate rocket and certify rocket performance and reliability. We support full-service missions, advisory services, and one-of-a-kind contracts. The Launch Services Program is the common thread that bridges the spacecraft organization to the rocket designer, and the spacecraft to the rocket. We provide long-term technical leadership and expertise from pre-mission planning to system verification and validation, all the way through launch. Whatever the vision or requirements, our team will be there, guiding our customers every step of the way on their journey through space. We are the common thread that connects the science world to the physical world by putting the necessary instruments in place. The thread that weaves NASA's industry-leading knowledge and support into the fabric of the commercial space market. We unite customers, capabilities, and culture to explore space through unparalleled launch services. NASA's Launch Services Program. We are Earth's bridge to space.
The Rescue Coordination Center started receiving distress signals.
The bridge was starting to fill up with water. The ship was sinking and got them out on top of the rescue boat.
Winds up to 60, 70 knots.
We started to separate one by one.
Wave height 50 to 60 feet.
Finally, I was alone and no rescue boat or nothing. The rescue boat drifted away.
It's freezing out there.
All I had to do was just wait and hope some kind of miracle would happen.
There is almost no chance to survive in conditions like that.
AIS, the automatic identification system. All ships out on the open oceans are obliged to transmit their position and their identity and their direction of speed, heading and speed, etc. It's kind of like air traffic control for the sea.
It's very useful to help provide assistance to ships in distress.
First of all, to see, do we have assets in the area that could help somebody in distress. In the days before AIS, we didn't even know if there were any vessels in a particular area where we have an incident.
They were more or less invisible to the Coastal Traffic Administration.
But as of today, If we have an incident out in open water, we have the chance to see what vessels are in the area and could contact them directly to route them to the position or the distress. And in that way, in a more effective way, rescue more people within a shorter time frame than we ever have before.
AIS receiving stations along the coast, they can only look a certain distance out into the sea.
Ships that go out beyond 75 kilometers outside the coast were over the horizon and invisible to us. But if you think about these signals going straight, they go maybe several hundred kilometers out into space. And you know what circles around the Earth about 400 kilometers above us? The International Space Station.
The European Space Agency contacted the Norwegian Defence Research Establishment and gave them the opportunity to mount an AIS receiver on board the space station to test out this technology from space. All our calculations indicated that this should work, but we really did not know before we switched on the receiver on the space station. 1st of June 2010, the system was turned on.
The switch was flipped and the light came on and we were actually able to get the first data in. Yes, the instrument works.
We all got very excited.
And suddenly we could see a whole world full of ship data. It was I would say, a quantum leap really in our ability to look at global ship traffic.
It's like a blind man starting to see.
Yeah, it was a huge relief and great satisfaction to see.
So this brought a whole new dimension to the monitoring of ship traffic on the open oceans.
Nobody knew how many ships really are out there at any given time, and suddenly we had, if not the complete picture, then almost a complete picture.
On a typical day, the space station is observing about 30,000 ships out on the open ocean.
I was kind of overwhelmed, I guess, by the response this got. The space station really is an excellent lab for testing this type of technology.
This project demonstrates that the International Space Station is not just for science and astronauts, but it really benefits the whole mankind with down-to-earth applications.
Based on the AIS, we had another vessels in the area that we contacted who continued to the area, and they searched together with the helicopters. Nobody expected to find anybody surviving in that conditions. They actually spotted one man in the sea.
After floating in the North Atlantic Ocean for 4 hours, I was finally rescued.
Thanks to AIS data and AIS data from the space station, this lone survivor was rescued. A absolutely happy ending for him.
And luckily for technology that made something that was basically impossible to survive possible.
What happens if you wake up in the morning and you understand the state of the world as it is right now?
What could that data enable? How could people make smarter decisions? How could, for example, a farmer get better yield on his or her crops? How could somebody help disaster response? How can we use satellites to help humanity? That in many ways was the underlying thesis of doing Planet Labs, was to get data into the hands of people that could enable us to make smarter responses to that.
Planet Labs set out with the mission to photograph the entire Earth every day. And they thought, how are we going to do this? They said, let's build our own satellite.
Commercial imaging satellites, they're very large. They are very expensive. We took a different approach.
By making them really small, we can launch lots of them, and by launching lots of them, we can cover this, to get to this mission of imaging the whole Earth every day.
If we can do that, then we can literally change the way that we see the world.
And they called it the Dove. It's about the size of a loaf of bread.
Our doves are basically mainly a big camera with a telescope looking down to take pictures of the Earth. We initially developed the first Dove satellite in our garage. So we kept on iterating the Dove design, we made it better and better, and eventually we put our first one into space. We had no idea what the quality would be like.
I mean, we didn't know if it was going to work.
But we got an image down and it was so beautiful that we knew at that point we could make this technology work.
Wow, we can really do this, and we can achieve this mission, which is something that is really needed for us to understand global change.
So we had done a couple of demonstration satellites, but the next steps we wanted to do was to scale it up, to test the first fleets of satellites.
But what made that possible was actually access to space.
So here's the problem, that in order to take pictures of the entire Earth every day, you're gonna need more than 1 or 2 satellites. You're gonna need a whole lot of satellites, and you're gonna need to be able to deploy them really fast. And really, there's only one obvious choice on how to deploy that, and that's the International Space Station.
There was no other platform in the world in order to get access to space of that fashion in that time period than the International Space Station.
NanoRacks is our key partner with NASA.
At NanoRacks, we understood Planet Labs' vision, and we knew that we could help. We worked together to figure out what was going to be the best way to get as many satellites as possible, and we basically developed a new platform. It goes out of the GIM airlock. It's picked up by a robotic arm, pointed out into space, and it fires these little satellites off of the space station.
They were able to secure 28 of our satellites to be launched from the International Space Station, and that was known as Flock 1, our first constellation.
This opened up the whole world to satellite developers, people that could put things into orbit fast.
We now deploy these on a regular basis from the International Space Station. And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The International Space Station does enable young, small companies like ourselves to get going in space.
The ISS provides a lot of opportunities for commercial companies to test and find where the market in space is going to be.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
The first pictures now coming in from Puerto Rico after taking a direct hit. Hurricane Maria slamming into the island. One official saying the island is destroyed.
Hours with winds and rain, and didn't stop.
Power lines are down. Streets are impassable. Many roads are flooded.
High winds uprooting trees, overturning cars, and turning buildings into piles of twisted metal.
It is something that will change Puerto Rico forever.
We had no water, no food, no gasoline, no communication at all.
Not knowing where my next meal will come from, it hasn't been easy.
After Hurricane Maria, everything was gray, all the plants were dead. Hurricane Maria took the color away from us.
I am sure that these children will not be the same. They will not be the same. They are still struggling and trying to recover from this.
My name is Joe Acaba. I'm a NASA astronaut of Puerto Rican descent. I was about a week into my mission on the International Space Station. Hurricane Maria was forming up, and from there, if you looked out the window, Maria took up a big chunk of what we could see. It was gonna cover the entire island. After the hurricane, their power grid was pretty much taken out. You just couldn't see the island anymore. The hurricane, I think, had a huge impact on, the island as a whole, but especially the kids.
Joe Acaba was our hero, and we need something positive. The students need something positive.
We wanted to pull through, forget all that happened, and
lift up our spirits and lift off the island.
So I knew I couldn't do much from up on the International Space Station, but I did want to connect with the students to show them that there is hope and that there are people out there that care about them.
NASA has the STEM station, which allows the students and teachers to talk to the astronaut in the space station.
It's making that connection so that maybe, they become more interested and we can inspire them more to study the STEM fields.
So we were able to establish and coordinate with NASA one of these video conferences. Thousands of students from different parts of the island watching the video conference with the space station, talking to Joe.
This is Joe aboard the International Space Station. I have you loud and clear. How do you compare?
What is the most impressive? How did Puerto Rico look?
Are astronauts allowed to visit? How often?
What is the minimum number of?
It was awesome because, as soon as it came up, you could hear people clapping, people were excited. So even though I couldn't see them, I could feel them, and that was pretty neat.
It was amazing. He called from the International Space Station to see how Puerto Rico was doing, and that means a lot for us, a lot.
In May of 2018, I was able to go back to the island, my first time since the hurricane. It was a great opportunity to get out and kind of come full circle with those students, to go and see them in person and, kind of reiterate how important they are and just to give them a little bit more hope because there's still a long way to go on the island.
He's a hero for us. Kids love him and everybody loves him here. Joe Acaba is the role model that we need at this time.
I want to be like him. I want to go far, and I want to be an example for little kids when I'm older.
Not only is the International Space Station a great tool for scientific research and exploration, but for students from Puerto Rico in particular, I think that having that video conference with them, it did provide some hope. It did provide some inspiration. And so it's just one of the benefits that we get from the International Space Station.
In order to support International Space Station, we're constantly having to build new hardware to send to space, but as well, we need to make training hardware on the ground. So we ask ourselves, what if we got high school students to build us some training hardware and get them out of the textbook, get them some hands-on lessons to work with, and by doing that, we'll be inspiring the next generation of students. So that's when we decided to create Hunch. Hunch goes to the local high schools, partners with the high schools, and gives these students opportunities to design, build hardware that will fly in space or be used for training hardware on the ground. Students did the design and engineering, the CAD drafting, the 3D print prototyping, the machining, the procurement of the hardware. All this done by high school students to get this article to fly in space. From the quality perspective, the students have exceeded all of our expectations. The hardware we're getting in is top-notch.
This program actually helps them focus into the engineering and the STEM fields.
I've been teaching for 23 years. I've never seen anything that even remotely compares to having the type of impact on students that Hunch has had. Absolutely phenomenal.
Working with the Hunch program, we fabricated training hardware for the ISS.
I created and designed interactive simulations.
We're making a Mexican paella and hopefully gets chosen to go to the International Space Station.
From the Hunch program, I've learned how to use AutoCAD.
We learned a lot of teamwork.
I've definitely gained some communication skills.
We're learning more about food science, technology, but everything basically doing this.
It gives them a confidence that I don't think they would have had to that level before this.
Maybe I would actually be able to be an engineer. So it was never something that I'd thought that much about. And then I was working on this stuff that went to space, and I couldn't think of anything more exciting. And I still can't.
It's a pretty cool thing to be able to tell other people or family when you go visit that I work with NASA programs.
I mean, I told everybody, like literally everybody.
We have an opportunity here for them that is unbelievable.
It's kind of like getting a master's at age 16.
They truly have moved on to a level they wouldn't have approached or wouldn't reach, I believe, without this program and without the International Space Station.
Before the Hunch program, I really was just a C student with no direction in my life. And since then, I've been on the Dean's List for the past 4 years and will be transferring to pursue mechanical engineering.
It really helped me find my passion for aerospace. The Hunch program gave me my career.
The impact on their lives has been amazing. They're more successful, they're more driven, they're more determined. They know they can achieve. And that's all, I think, through this program, through the Hunch program and interaction with the International Space Station.
Today's telescopes study the sky across the electromagnetic spectrum. Each part of the spectrum tells us different things about the universe, giving us more pieces of the cosmic jigsaw puzzle. The most powerful telescopes on the ground and in space have joined forces over the last decade in a unique observing campaign known as GOODS, which reaches across the spectrum and deep back into cosmic time.
Hello and welcome to this very special multicast. We'll be exploring a unique collaboration between some of the world's most powerful telescopes, both on the ground and in space. Now to do this, we've set up a similar collaboration between the ESOcast, the Hubblecast, the Spitzer Space Telescope's Hidden Universe, and the Chandra X-ray Observatory's Beautiful Universe.
I'm Megan Watsky for the Beautiful Universe from the Chandra X-ray Center.
And I'm Dr. Robert Hurt for the Hidden Universe from NASA's Spitzer Science Center.
It's the combination of deep observations from many different telescopes that makes this project so important.
The longer a telescope spends looking at a target, the more sensitive the observations become, and the deeper we can look into space. But to get the full picture of what's happening in the universe, astronomers also need observations at a range of different wavelengths, requiring different telescopes. These are the key ideas behind the Great Observatory's Origins Deep Survey, or GOODS for short.
The GOODS project unites the world's most advanced observatories. These include ESO's Very Large Telescope, the NASA ESA Hubble Space Telescope, the Spitzer Space Telescope, the Chandra X-ray Observatory, and many more, each making extremely deep observations of the distant universe across the electromagnetic spectrum. By combining their powers and observing the same piece of sky, the GOODS observatories are giving us a unique view of the formation and evolution of galaxies across cosmic time, and mapping the history of the expansion of the universe.
Now this is not the first time that telescopes have been used to give us extremely deep views of the cosmos. For example, the Hubble Deep Field is a very deep image of a small region of sky in the northern constellation of Ursa Major. This revealed thousands of distant galaxies, despite the fact that the whole field is actually only a tiny speck of sky, about the size of a grain of sand held at arm's length.
Now, with GOODS, many different observatories have brought their powers to bear on two larger targets, one centered on the original Hubble Deep Field in the northern sky, and one centered on a different deep target, the Chandra Deep Field South in the southern sky. The main GOODS fields are each 30 times larger than the Hubble Deep Field, and additional observations cover an area the size of the full moon.
These areas of the sky were already some of the most extensively explored, and so the combination of the existing archival data with the many new dedicated observations gives us an unprecedented view of the history of galaxies.
At ESO's Very Large Telescope on Serra Paranal, the 8.2-meter diameter giants were used for a total of almost 100 nights of dedicated observations. The telescopes made images of the region both in near-infrared light and on the boundary between visible light and ultraviolet light. At these short wavelengths, only telescopes on exceptional sites, such as the VLT's Serra Paranal, have a chance to observe through the Earth's atmosphere.
The NASA ESA Hubble Space Telescope observed the goods regions at optical and near-infrared wavelengths in order to detect distant star-forming galaxies, among other things. Now, Hubble spent a total of 5 days observing the fields, spread over 5 repeat visits. Each of these was separated from the previous one by about 45 days. Now, by spreading out the observations like this, Hubble was able to watch out for new supernovae appearing over the months, providing key information for studying the expansion and acceleration of the universe due to the mysterious dark energy.
But it wasn't just Hubble making space-based observations for goods. NASA's Spitzer Space Telescope imaged the goods regions in near and mid-infrared light for 5 days at wavelengths up to 30 times longer than the Hubble observations. These longer wavelengths are important for revealing distant galaxies whose light may be obscured by cosmic dust or stretched by the expansion of the universe, making them invisible to Hubble. For these distant galaxies, the Spitzer images also tell astronomers about their age and their total mass of stars, complementary information to the data from Hubble. Now, let's move from the infrared to much shorter wavelengths.
Also in orbit, the Chandra X-ray Observatory had already observed the goods field in many long observations taken over the course of a year. The Chandra images are the deepest X-ray images ever taken and detected more than 200 X-ray sources believed to be supermassive black holes in the centers of young galaxies. The X-rays are produced by extremely hot interstellar gases falling into the black holes.
These multi-wavelength observations identified tens of thousands of galaxies. To get a full understanding of the history and development of galaxies over the vast stretch of the universe's history, we need to be able to pin down their distances more precisely, to fix them in cosmic time. As these galaxies are so far away, the light waves we see from them today started their journey up to about 13 billion years ago. And because the universe has been expanding since the Big Bang, back then the universe was less than 1/7 of its current size.
During the billions of years of the light's journey, its wavelength has been stretched as the fabric of space has expanded. This effect is known as redshift because, for example, light that was originally blue or ultraviolet in color is shifted to longer and redder wavelengths.
Back on the ground, astronomers used spectrographs on ESO's Very Large Telescope to capture the spectra of galaxies, spreading out their light like the colors of a rainbow. Now, the spectra allow astronomers to measure the redshifts of the galaxies and hence their distances. An extensive campaign produced redshifts for almost 3,000 galaxies in the goods fields. Now, with this knowledge, we can place the galaxies at their distances along a vast cone of space, stretching out from our own vantage point like a searchlight beam into the cosmos. We can take an amazing journey through kind of a tunnel towards the edge of the universe. In some places, the galaxies cluster together, forming structures which are up to tens of millions of light years in scale.
Thanks to goods and other surveys of the same region, these areas of the sky are uniquely well studied, with high-resolution, deep observations across a wide wavelength range. Plus, there's more to come. For example, the Atacama Pathfinder Experiment Telescope, or APEX, has spent a total of 300 hours, nearly 2 full weeks, imaging the region at submillimeter wavelengths from its high site on the 5,000-meter altitude plateau of Chajnantur in the Chilean Andes.
Observations at these wavelengths are ideal for finding the redshifted light of distant, dusty galaxies in the very early universe. Because of the longer wavelength of its submillimeter light, The apex image is not as sharp as the visible light and infrared images. However, thanks to the deep Spitzer images, as well as images made at radio wavelengths, we can match up and identify the objects found by apex with galaxies seen at other wavelengths. The sub-millimeter light glow reveals that hundreds of stars are being formed per year in these galaxies. In the next couple of years, ALMA, the Atacama Large Millimeter Submillimeter Array, currently under construction on the same plateau as APEX, will begin its first science observations. Also observing at submillimeter wavelengths, it will have much greater sensitivity than APEX and resolution even better than Hubble. ALMA will revolutionize our understanding of the early universe by revealing many more distant, dust-obscured galaxies that cannot be seen at all by visible light and infrared telescopes.
These projects are an excellent example of how great observatories are joining together across the electromagnetic spectrum to give us a more complete view of galaxies over the history of the universe. Already, astronomers have written over 400 papers based on these data, with even more in the pipeline. And on top of that, the observations of the goods fields will continue in the future. These patches of the sky will be prime targets for the next generation of telescopes, both on the ground and in space. And astronomers around the world will use these data to learn new things about the universe for many years to come. Saying goodbye to our friends at the other observatories, this is Dr. J, signing off for the ESOcast and the Hubblecast.
This is Dr. Robert Hurt signing off for the Hidden Universe and the Spitzer Science Center, reminding you there's a hidden universe just waiting to be discovered.
And this is Megan Watsky, signing off for the Chandra X-ray Observatory and the beautiful universe.
Join me again next time for another cosmic adventure, which I'm sure will surprise us beyond our wildest imagination.
Our planet is a living example of a delicate balance. A complex system that is constantly changing, constantly evolving, constantly adapting. How do these changes affect life on Earth? How does everyday life affect our planet? We have a great capability to absorb, interpret, and comprehend, and an urge to understand the world we live in. This is what defines us as human beings, what makes us who we are. With our technological advancements, we are now capable of exploring new worlds, new frontiers. We're searching for answers that may lie in front of us. Better yet, above us. The field phase of the experiment is about to begin. All the planning, sleepless nights, meetings, and hard work the team has invested in the mission are at stake. My name is Jasna Pittman, and I'm one of the many scientists working on the airborne tropical tropopause experiment.
Very natural for humans to want to understand how the world around us works.
Why the atmosphere does what it does, it's like solving a puzzle. You just want to understand how it works.
We're trying to understand how we're affecting, how humans are affecting the atmosphere.
Understanding how the stratosphere changes very much reflects how our climate is changing.
I think that the work that is done in atmospheric science is very important, but it's also a lot of fun.
It's like the best job possible.
Well, NASA has been doing airborne science investigations for quite some time. Some of the earliest investigations we were doing was related to the early days of the Antarctic ozone hole.
In 2009, we started a new kind of program. It's called the Earth Venture Program. It's got 3 parts, and the first of those parts is what we call suborbital science. This is science done not using or not including a new satellite.
With some of these newer missions, we have let the community come up with their own ideas, their own way of implementing the mission, what their own science requirements are, and they bring their measurements to the table.
And ATREX had very good science, was very relevant to the kinds of questions we wanted answered, and its budget was reasonable and appropriate.
ATREX is an airborne campaign to try to understand how stratospheric water vapor affects climate.
It causes perhaps maybe 15 to 20% of the warming that we've had in the past 15 or 20 years.
So it turns out that small changes in the humidity in the stratosphere are very important for climate and important for surface temperature. They're actually comparable to the importance of greenhouse gases that everybody knows about.
So for example, we know that if you go back 30 years, carbon dioxide was quite a bit less 30 years ago. Methane was less quite a few 30 years ago. Nitrous oxide was less 30 years ago. So we know these gases are increasing with time.
Gases that affect the chemistry of the stratosphere, which is where the ozone layer exists that protects us from ultraviolet radiation.
So understanding the rate at which this stuff gets into the stratosphere and how it changes is extremely important to looking at the climate of the stratosphere and how the stratosphere climate affects the lower atmosphere.
So we really need to understand what controls the humidity of the stratosphere and actually be able to predict that in the future in order to improve the accuracy of our predictions of future climate change. Turns out the most important place to go sample to understand that is the tropical upper troposphere, the top of the troposphere in the tropics. It's called the tropopause, which is actually a very high altitude, which is why we need a high altitude aircraft to study it.
So the tropical tropopause is at about 55,000 feet in the tropics. So if you go down to the equator, you have to go up quite high, above 50,000 feet. And the tropical tropopause is really important to the global atmosphere because most of the gases that get into the stratosphere, all the air that's circulating upward into the stratosphere goes through this tropical tropopause region.
So that's basically a gateway to the stratosphere. The general circulation transports air upward in the tropics, goes into the stratosphere, and then is spread throughout the stratosphere and comes down at the higher latitudes in the polar region.
And this is what ATREX is focused on, to look at that motion of air into the stratosphere and how the water is removed from that air as it rises upward.
We know a lot about it. but there are some puzzles about the details of how the clouds are formed and under what conditions they form. So that's probably the most important thing that we hope to gain from ATREX.
ATREX will address a number of really important issues. It'll give us a better understanding of exchange between the troposphere and the stratosphere and how that impacts atmospheric composition, how that affects the chemistry that goes on in the upper atmosphere, and in the longer term, how that will affect climate.
And that will help us to understand as we go forward with trying to figure out what to do about climate change to better predict it and make better decisions.
How does the interaction between the upper troposphere and the lower stratosphere affect us down below? How are we going to find out? We have the questions. Now we'll be searching for the answers. Hawks' sense of hearing is excellent, and their eyesight the best in the entire animal world. Not only can they see greater distances than humans, but their visual acuity is 8 times that of ours. Yet we need to look even further, higher, deeper into the sky.
We live in the lowest layer of the atmosphere, which is the troposphere. The stratosphere is the next layer above us, so it's basically above altitudes of somewhere between 30 and 50,000 feet.
There are processes that take place in the stratosphere that have very direct impact on us.
So it's extremely important to understand the detailed process of water turning into clouds, those particles in clouds settling out. How does that detailed process occur, and then how will it change in the future?
What's been our big problem is getting the airplanes to the right place where they can make the measurements for long enough periods of time to do the observations.
So it turns out the Global Hawk is a perfect tool for sampling this part of the atmosphere. It's a high-altitude aircraft. It flies considerably higher than normal commercial aircraft, but it's also got this extremely long range.
So our bird here can climb to a cruise altitude of 65,000 feet and fly for up to 30 hours.
So we can basically, for example, we could fly from here to Australia in one flight.
So the basic geometry of the airplane, it has a wingspan of 116 feet, which is equivalent to the wingspan of a Boeing 737 transport aircraft, a length of about 65 feet, weighs about 27,000 pounds, fully fueled at takeoff.
In comparison, in the past, people have used manned high-altitude aircraft like the ER-2 or the WB-57. However, those have very short range.
Now that we have the Global Hawks, they have a much longer flight duration. They can get to these key areas to appropriately attack the science questions that we've been thinking about for a very long time now.
Basically, for this program, we searched out the best instrumentation, the best expertise in making these measurements, and invited them to be part of the program for the proposal for the ATREX mission.
Once the major science campaign, the project mission scientist, selects the instrument teams, that's really when our work gets started. We will then visit them and begin coordinating all the mechanical and electrical interfaces we need to do to get them mounted on the airplane.
You have to determine everything from the size of the instrument, so you know how much space it's going to occupy or needs to occupy in the aircraft, how much the instrument weighs, so you can be sure that what you design mechanically for installing the instrument on the aircraft is of sufficient strength to be able to hold the instrument in the aircraft.
In some cases, you'll see probes sticking out of the airplane, so all that has to go through aerodynamic analysis, etc. Structural mounts inside have to be properly stress analyzed, so we make sure all that happens. So we coordinate with all the proper technical fields to get ready for the instrument to arrive here.
From the time we first start communicating with the instruments teams until we're ready to actually start performing science with all the instruments on the aircraft, it takes about a year and a half of really hard work, close coordination, and a lot of good communication between everybody.
We're using state-of-the-art instruments, or cutting-edge instruments, to measure things like water vapor, clouds, and temperature, and a whole bunch of trace gases.
We have a very sophisticated instrument called the Cloud Physics LiDAR. It's a laser, shoots out the bottom of the nose of the plane, and as the laser goes down, some of the light gets scattered back, and there's a telescope that collects that light. And because you know how long it takes the light to go down and then come back up, you can tell what kind of cloud structure there is below the plane. So if we see very thin clouds, this laser can detect those very thin clouds. We have a meteorological system on board the plane that measures winds, temperatures, and pressure. And it's the best meteorological instrument in the world for measuring these. Imagine how hard it is to measure from a plane that is going a few hundred miles per hour. So it's a really hard measurement to make, and they do it. We have water vapor measurements, 2 water vapor measurements on board the plane. Water vapor is important to look at how air that's going into the stratosphere gets freeze-dried, so you have to have a really high-quality water vapor measurement, and we have 2 instruments to do that. We measure ozone on board this plane. Ozone, as I mentioned, the ozone layer screens ultraviolet radiation, so we have to know what the ozone looks like. There's actually very little ozone in the lower atmosphere, and there's a lot as you get into the stratosphere. So we use ozone actually to tell us the difference between stratospheric air and tropospheric air. We have another instrument that actually sucks little gas samples, has little cans, so it'll suck in a little air, and then you bring those cans back, take them to a lab, and you could literally measure 100 different gases from these little gas sample cans. And that's really important because you can look at all sorts of natural and human-produced gases to look at things like ozone depletion and climate change.
So all of these will tell us how air is transported through the tropical tropopause region and how it's dried to the very dry conditions of the stratosphere.
ATREX is sort of a pathfinder in terms of investigating some of these processes, and when I say pathfinder, it's utilizing a brand new tool, and that is the Global Hawk.
This is a hybrid. It's like a satellite that you control from a control room, like a mission control, but it has nobody in it, like a satellite. So it's really a new and revolutionary way of doing science.
With the science that we do at NASA, we need to combine the satellite data with aircraft data, with modeling data, and even some measurements from the ground all together to answer the science questions the right way.
In 50 years, we'll look back on this plane, and it'll be very common, it'll be used all over the world. I really believe that planes like the Global Hawk are going to change atmospheric science in a very profound way, and for the betterment of everybody who lives here on the Earth.
Everything is ready. We should be airborne soon.
On a remote peninsula in the South Pacific, a rocket and 10 small satellites are about to launch a new era in spaceflight. Rocket Lab's Electron rocket is a new player in the space arena, and those tiny spacecraft, called CubeSats, represent big dreams.
It's kind of like the preeminent, most exciting mission within the whole company. The whole team is just incredibly excited to have that NASA logo on the side of the vehicle and fly those payloads.
The NASA payload about to launch on the Electron rocket is called ELANA 19. ELANA stands for Educational Launch of Nanosatellites, part of NASA's CubeSat launch initiative. This is the agency's way of providing a path to space for CubeSats, compact satellites that pack a lot of science into a package about the size of a loaf of bread.
Space is no longer just for high-value science or the intelligence community. It is a place for a payload that you can create that can get up to space.
Until now, CubeSats have always launched with larger spacecraft, but flying as a hitchhiker limited where they could go and the science they could do. That's what makes this Rocket Lab flight so historic. It's the first time these small satellites are the stars of their own show, flying on a rocket designed for their needs. The 10 CubeSats flying on ELANA 19 were developed by teams from across the nation, from high schools and universities to NASA field centers. Da Vinci was developed by a student-led team at North Idaho STEM Charter Academy. It's designed to connect to students around the world by broadcasting education-related messages through amateur radio in Morse code. It also carries a Global Star modem and ArduCam, allowing users to upload digital messages or see photos of Earth from orbit.
I don't know if anyone remembers like the Ovaltine messages and stuff on the radio way back when, but our goal is to do something like that where they have to tune in every week or every other week to get this new message and decode it and really dive into that information so that they develop an interest in space and they say, oh, hey, I can communicate with something that's not even on this planet.
RSAT was developed by a team of midshipmen from the U.S. Naval Academy in Annapolis, Maryland. This crab-like CubeSat has a pair of robotic arms designed to grab a host satellite and maneuver around it to take photos, or potentially even make repairs if a spacecraft isn't working properly. The CubeSat STF-1, or Simulation to Flight 1, is a collaboration between NASA Independent Verification and Validation Program with West Virginia University and small businesses. STF-1 will monitor space weather over Earth's poles and test the durability of new materials for use in LEDs. But it's also designed to demonstrate a simulation and test platform to aid in the development of future CubeSat missions. These CubeSats show that small satellites have an important and growing role in space exploration. NASA's Venture Class Launch Service was created in 2015 to provide CubeSats their own ride to space, expanding launch and science opportunities for small satellites and sparking a brand new segment of the space launch industry. Rocket Lab's Electron rocket is one of 2 vehicles NASA selected for Venture Class missions. It's smaller and lighter than other launchers in NASA's stable, but that's the whole point.
The intent is for the Venture Class launches to occur at a rapid pace that match the iteration and design cycle that CubeSats can go through. So instead of having a launch for a primary mission once every 2 years, once every 5 years, the real goal is to see Venture Class rockets get to a cadence where they can see regular access to orbit.
Many of the CubeSats on the ELANA 19 mission are designed to benefit future missions. Shields 1 was developed by NASA's Langley Research Center in Hampton, Virginia. Its objective? to test materials that could be used to shield spacecraft against radiation.
This is a